Ray, and thanks to the organizers for really a great workshop. It's been very educational, a lot of exciting developments in a field that started a long time ago. It's good to see a lot of younger people making some incredible progress on problems that we couldn't solve in the old days. All right, so I'm going to talk about some work in collaboration with a number of people, so I should just mention them at the outset. Ilya Estelitz is at Wisconsin. How you go, I think he's here. At Cornell, Avishkar Patel from Flatiron, and Avishkar has given some talks earlier in the workshop, which will overlap a bit with what I'm going to say. Chen-Yuan Lee, a current student who's moving on to Rice. Davide Valentis, he's a postdoc of Jörg Schmalian at Karlsruhe, and Peter Lanz, who also spoke earlier in the workshop on some of these things, who's a postdoc at Harvard. Okay, so let me just begin by recalling the basic, what's sometimes called the Hertz-Millis theory of quantum phase transitions. And all of these phase transitions are phase transitions in metals. And the basic structure is that there's some change in the Fermi surface due to the phase transition. So that itself could be, if you wish, an autoparameter. So the simplest possible change you could imagine would be some kind of distortion from, say, a square-like Fermi surface to a rectangular Fermi surface. Then there's some Ising autoparameter associated with this because there's two possible orientations of the rectangle. And that's called the Ising nematic order. You can represent it by a scalar field phi, an Ising field. And the basic theory is the theory of this Ising field coupled to the Fermi surface. And there's kind of a three-point Yukawa coupling that ends up where the Fermi surface ends up damping the Ising field and changing the nature of the phase transition. Okay, so that's the basic structure of Hertz-Millis theory. And then there's a phase transition here at zero temperature, which presumably controls a quantum critical region at finite temperature. So that's type 1. Another one I'll call type 2, where there's an autoparameter at finite momentum, like, say, a spin density wave autoparameter. And then there's a reconstruction of the Fermi surface, but the basic structure of the theory is essentially the same. But more novel is the type of phase transition where there's no autoparameter, so no broken symmetry, but nevertheless there's a change in the shape of the Fermi surface. And that can happen if there's some kind of spin liquid that's present in the background to allow for the violation of the Luttinger relation. So this is a jump in the size of the Fermi surface. So in this case, the theory is a bit different. There's a Higgs field phi that drives this phase transition. And there's also some spin-ons around that have to be present to account for the Luttinger theorem. And there's a gauge field. So it becomes rather more complicated, at least in the clean limit. So these three types of phase transitions have been studied thoroughly over the last 2 or 3 decades. And there were many talks in the workshop on these phase transitions, all in the clean limit without any disorder. So what I'm going to argue today is that once you put in a certain type of disorder, in fact, all these three theories basically become the same, and you get essentially the same properties, which in fact relate to many experimental observations. All right, so what we know about this theory in the clean limit, that there is, in all three cases, some kind of non-Fermi liquid at the quantum critical point with the breakdown of quasi-particles. But when you go to finite temperature, you'd expect this state to be a strange metal, as it's seen in many experiments. But it's become clear over the years that, in fact, it's not a strange metal. It's a perfect metal, having to do with conservation of momentum in the long wavelength limit. So there's been a lot of work on this. I spoke about this at the meeting last year, so I won't say anything about this today. There's also many talks on this. There was a nice talk by How You Go last week on the effect, on the nature of transport in these clean non-Fermi liquids. So however, as you all know, experimentally you do see some remarkable phenomena near one of these quantum phase transitions. So this is the resistivity data of Nigel Hussey's group in lanthanum strontium copper oxide. And there seems to be a quantum critical fan, but also famously what's called the foot where the quantum critical linear T resistivity seems to extend over a wide range. Okay, so the theme of my talk will be to argue that all of this phenomenology can be understood when you take one or more of these universality classes and you add in spatial randomness. And the spatial randomness Harris disorder, what do I mean by Harris disorder? It's simply a disorder that moves the position of the quantum critical point. So one side of the sample could be to the left of the critical point, the other side of the sample could be the right, and that fluctuation is extremely important in determining the nature of the quantum phase transition and also the transport at finite temperature. So the final story, in fact, will be somewhat subtle. It took a few years for it to come together, but the answer is really very simple. The answer is that when you're in this higher temperature regime in the so-called quantum critical fan, then this boson and fermion excitations of the Hertz-Millis theory basically both remain extended. And so because they're extended, the effects of disorder is rather mild and can be taken into account in some kind of self-averaged way. And we've learned how to do that over the past few years in metallic states, how to self-average disorder in strongly interacting fermions in the context of the SYK model, or what's called the Yukawa SYK model, where you have both bosons and fermions with random interactions. And I'll show you that if you take such a theory, you can really understand many details of the observations in strange metals across many different systems. However, there's also the foot, this foot down here, and I'm going to argue that this is due to localization, but not localization not of the fermions. The fermions remain extended. Localization of fermions or Anderson localization is a rather weak effect in 2 dimensions. I'm assuming here the disorder is relatively weak, so we're going to ignore that effect, but the localization of bosons is much more important, and that's what's responsible for this foot. At least that's the claim. Okay, so let's jump right into the low temperature regime first and argue why is it that the bosons localize due to Harris disorder. Okay, so this is recent work with Avishkar and Peter. Yes?
Can you remind us what this boson is?
Yeah, well, so the boson is this field phi here. So it could be, depending on whether you're in type 1, 2, or 3. In this case, it's the Ising order parameter. In this case, it's the vector order parameter. And in this case, it's the Higgs field. Okay. Here you're coupled to a gauge field, but somewhat remarkably, the gauge field doesn't make much of a difference once you go into the random case.
Should I think of it as a parton of the fermion?
Yeah, it's more like an exciton. It's a particle hole composite. It's like a parton which combines the spin-on with the electron. So that's why it carries a gauge charge also. Yeah.
In what cases should I also expect disorders to lead to random field disorder from my...
Well, sure. So I won't treat random field disorder. Thank you for that question. In this case, it's rather hard to have random field disorder because that will violate gauge invariance. But in this case, some magnetic moment will give you random field. Or in this case, anything that breaks the 90-degree rotational symmetry will give you a random field. So that I will not consider. So that's why the Harris disorder is precisely to exclude that. All right, so as I said, I want to talk about this low temperature regime where the bosons are extended, or localized, excuse me, but the fermions are extended. So let me show you why that happens. And the simplest way to see this is to just go ahead and assume that the fermion disorder is rather weak, and we're just going to take a theory of the bosons alone. So let's discuss the kind of theory we have. So this is the Hertz-Millis theory, where you have a Fermi surface psi coupled to some boson or scalar field phi. With this is the mass term which tunes the quantum critical point, and this Yukawa coupling G. And so there's some Landau-Ginzburg theory for phi, and the Yukawa coupling to a Fermi surface. So there's various indices here that will change depending on which case you're looking at, and I've dropped all those indices. All right, so now what are the types of disorder you can add? Well, the most familiar one is just a random potential here in blue that acts on the fermion density. And this is the basis of the theory of disordered interacting metals and leads to, all those weak localization effects, which I'm going to actually ignore. That's assumed to be very weak. But the elastic scattering, just the bond scattering from V, will be important in the analysis. So you can just treat this in the bond approximation. However, the other Harris disorder is a disorder in the boson mass, delta S. So we'll just take that to a random variable. And if you do some fairly simple Harris-type argument, you'll see that delta S is a strongly relevant perturbation. So unlike V, or the localization effects here, which are marginally relevant, this is strongly relevant, dimension order 1 or something. And so this is the thing we have to account for first. That's really the key to the whole analysis. All right, so how are we going to account for it? For now, let's just assume that the fermions are extended, and we just integrate them out. So then you get the essential Hertz-Millis theory, where you have the scalar field phi, and the presence of the fermion leads to this damping. This is the Landau damping. And in all three cases, they're just mod omega due to the presence of this random potential V. But then the important thing is this random mass, S prime, that we want to account for. So now the key is that the interactions in the damping can be treated somewhat perturbatively, but you have no choice but to account for this random mass exactly. You have to really do the whole thing numerically. So that's what we're going to do. We're going to account for this random mass exactly, but everything else is, at least to begin with, will be approximate. Yes? That's because of the random potential V. So there's some elastic scattering length of the fermion. The mod omega over Q becomes mod omega over the mean free path of the fermions. Anything else?
Are you going to keep both omega and omega square terms?
That is just for a cutoff, yeah. I mean, you can put a hard cutoff if you want. This just makes the thing. But the important part is the mod omega. All right, so all we've done here, and this is similar to work that Adrian Del Maestro did in one dimension for disordered superconductors with pair breaking, is that we just treat the interaction U in the Hartree way. And the point here is that, when there's regions of negative S, phi will want to condense in that region, and to prevent a runaway instability, you have to put the U in. So this S prime will become S bar prime, and S bar prime has to be computed self-consistently by solving this equation, and this is where the mod omega comes in, and it actually changes the behavior due to the strong influence of the low energy modes. Okay, so Avishkar essentially using some fancy GPUs solved this in rather large samples, and I'll just show you the results. So, for example, you can measure the correlation length of the boson as a function of the coupling S, and you see this very nice crossing point telling you that there's a quantum critical point right here. Then you can sit at this quantum critical point and look at the structure of these eigenfunctions. So these psi's are the eigenfunctions, sorry for the not correct notation. Psi is the eigenfunction of the boson propagator. No, it's not the fermion. Excuse me. Okay. So basically, psi alpha are the eigenvalues of the quadratic form for the bosons from the random, self-consistently determined random mass. So if you look at the eigenfunctions and look at the localization length, so this is, once you have the eigenmodes, you can compute the participation ratio and get a localization length. I think this is on a 160 by 160 sample. And so you see this remarkable non-monotonic behavior. And so this graph is the heart of everything I'm telling you about. So out here, when the localization length is practically the system sample, the size of the system, then the eigenmodes are completely extended. So these are the bosonic eigenmodes. In the Hertz-Millis theory, they'd be plane waves. Here, because of random mass, they're kind of plane waves with lots of random phase shifts. And in the second part of my talk, I'll talk about how you deal with this in an analytical way that allows you to get really results in closed form. Yes?
How much of this is special to, it seems like the only way the fermions fermions that involve, let's say you have monomega.
Yes.
But because it's quench disorder.
Yeah. So, okay, so let me jump ahead. So this is an approximate calculation, but there's a, let me answer this question. There is this sign problem free quantum Monte Carlo by Peter and Avishkar, which I'm not involved in. Basically took the full theory with in this case, actually they put in a random coupling for reasons I'll explain soon, and just solve this whole thing completely with no approximation. And in this case, they look at the boson susceptibility. They put a magnetic field here and look at the response there. And you can look at the eigenmodes of the boson susceptibility. And then look at their localization length. And this is their result. This is a full calculation, which is remarkably similar to this mean field Hartree calculation.
But as a phase, if there were no fermions, can I think of it as just post-glass?
No, it's overdamped bosons. The mod omega gives you damping, so they're not, yeah, Bose-Glass, it's a little different, yeah. Those are long-lived particle excitations, but localized, yeah.
Are they dispersal bosons?
Sure, I mean, there is this hopping term here, that's dispersion.
But it's so consistent condition.
Well, that dispersion comes into the eigenfunctions. So you have to look at the eigenmode of this operator, and that determines the eigenfunctions. Yeah.
What's beta?
Beta is inverse temperature. Which beta?
On the next slide?
Yeah, that's inverse temperature. System is 160 by 160, and this is the inverse temperature.
So why isn't the right space? You would like psi over L or some strange power?
Let's see, so Z is not 1 here, Z is 2. Oh? Yeah, well, this is the best fit. So here we just solve the whole thing. Yeah, that gives you the value of Z, or Z nu or something. Okay, so I was telling you about these extended eigenmodes, and we'll return to them later. And hopefully I answered your question that, yes, this is an approximate, but we are pretty confident it's essentially right. You had a question, Andre? Okay. All right, but now let's look at what's remarkable about this result is that as you lower in energy, the localization length goes down. So the boson seems to localize, but it's non-monotonic. So here, if you're at point C, then you have this localized boson mode. But when you go to even lower energy, notice this is a log scale. So this kind of energy resolution is only possible because of the GPUs that Avishkar used and the large values of beta. And so now you see this increase, very slow logarithmic increase in the localization length. So here you have just some localized mode, and then when you look at point D, you get these localized modes, but they have little patches here and there starting to couple together. So that should remind many people in the audience of what's called random singlet physics, and that's in fact exactly what's going on in here, we think. And so why is this non-monotonic? In fact, this logarithmic increase in the localization length was already anticipated by this very, very important paper by Hoyos, Kotobaji, and Thomas Wojta, who looked at essentially the same model we're looking at, but they also put in randomness in the boson dispersion, Jij, and randomness in the boson mass. So they looked at the case of very strong disorder, where you have large randomness in Jij and large randomness in Sj. And they derived, using a strong disorder Rg, a bunch of Rg equations for the couplings J and the coupling S. And remarkably, these are exactly the equations that Daniel Fisher obtained for the random transverse field Ising model. So ultimately, the very low energy behavior is for the random transverse field Ising model. Now, these are very different systems. Here you have an insulator with a discrete symmetry. Here you have a metal with a continuous symmetry, and they're the same. So why is that? Well, I could go into that in some detail. That's well understood, and our numerics support this result. because of a similarity. So in 1D, when you get a rare region, you're really looking at one spin effectively. So in this case, you have an Ising spin, just a single. So in the time direction, it's like a classical Ising chain. In this case, you have an XY or ON chain in the time direction, classical ON chain, but with a 1/r² interaction. And some of you may know that those are both systems that have an exponentially large correlation length at low temperatures. And that's why these two are essentially the same. Okay, sorry?
1/² from 1 omega.
Exactly, thank you. So I think that's our interpretation of what this is. And this exponent mu, then if this interpretation is correct, it should be the same as the exponent of the transverse Ising model, which was numerically studied in 2 dimensions. So we don't really know mu that accurately, nor can we claim to get mu that accurately, but maybe someday this can be tested more precisely. And so the quantum critical point, ultimately, the quantum critical point, if you ask what is this universality class, which is this critical point, we believe it's the random transverse Ising model. All right. So that's one of the important results here. I mean, again, it's not a new result. This was already there in Hoyos et al. We have now shown some further evidence for this. Okay. Yeah, so I already showed you the Monte Carlo results. So we can now also take this boson propagator and put it back perturbatively and compute the fermion self-energy. And you see sigma of omega, has a, if you look at it with a generous eye, has a quantum critical region here, and then some foot developing away from the quantum critical point. So there's definitely a strange metal phase down to low temperatures, coming for essentially the Griffiths effects of these localized bosons. You can also compute the resistivity, and near the critical point, it's linear in T, and away from it, it's fermi-liquid-like. Okay. All right. So I should also mention here some very nice work. In fact, I learned about this work at the KITP meeting last year, where this was a phenomenological model by Eresberg talked about it, where you imagine you have some strange metal with a bunch of 2-level systems or some localized bosons, which they treat in some SYK-like approximation, self-consistently coupled to some itinerant fermions, and they got, non-Fermi liquid behavior of various types, which depended sensitively on the distribution of the level spacing of the 2-level systems. So what we are getting is physics very similar, but we're not putting anything by hand. This is just the Hertzmiller's theory with random mass disorder, that's all. And it seems to, on its own, give you some physics qualitatively similar to these 2-level systems. Certainly it was this talk by Eres that inspired my thinking in this direction. Okay. All right, so now how about the higher temperature regime, where you have, we believe, we have now numerical evidence of extended bosons and extended fermions. How do you treat that? Okay, so what about this regime here? Can we do a more quantitative theory of what's going on here? All right, so let's go back to the theory we are considering. You have a random mass term, delta S, and a random potential V. And as I said, RG analysis shows that delta S is the most relevant disorder. So if I want to treat this analytically now I don't want to integrate out the fermions, but I want to treat the random mass in a, rather than, not, if you can of course now start to treat random mass diagrammatically, try to sum diagrams, just putting in the delta S. And you get total nonsense. It just doesn't, it's not sufficient to treat it in that manner. You have to treat it a little bit better. So how do you treat it better? Well, the point is you should somehow treat this delta S exactly. Now, if this was the only term around, it's very simple to treat this delta S exactly. You just rescale phi. So if you rescale phi, you can make this coefficient constant. But at the price of rescaling phi would be that other terms would acquire now some spatial dependence. Well, we know that most of those other terms, the spatial dependence is not as important as delta S, so we keep only the leading term. And the leading term is a Yukawa coupling. So you can account for the random structure of the eigenmodes of phi just by rescaling phi, or by, in another way to say it, you just transform to the basis of the extended states of phi, and then that will induce a randomness in the coupling, which we call G prime. So this is the theory we're now going to work with. The disorder, instead of being strongly relevant, now becomes a bit milder, and you can then treat this actually perturbatively, in the same way you can treat it in the SYK model. You have to do some self-consistent perturbative theory. So that's a bold step, but we believe on the basis of the results I've just described, it'll work as long as phi doesn't localize. If it starts to localize, then the randomness in K becomes extremely important, and that is exactly what Hoyo-Sotelo accounted for. Okay, so as long as these are extended, this should be fine. All right, so now we can just now turn the crank. These are the kind of theories we've learned to solve in some detail over the last 5-10 years. You just do self-averaged disorder perturbation theory. And in this case, because you have fermions and bosons, you'll get a bunch of self-consistent equations for the self-energies of the boson and the fermion. And so these equations are exact for certain SYK tape models. Here, for this model in 2 dimensions, you can make it exact by adding lots of flavor indices, which I have not done, and just say, well, this is the self-consistent theory we are solving, supported by the numerical analysis, both the quantum Monte Carlo and the self-consistent Hartree. All right, so now there's these blue terms are the terms due to disorder, and there's a G prime disorder and the V disorder, but there's also this coupling G, which is spatially uniform. So when you include the coupling G, then the problem becomes quite a bit more complicated, because the self-energies are functions of momentum also. And so solving these equations completely with both G and G prime non-zero has not been done, although it can be done. It will take some effort, and maybe someday we'll get around to it. But right now I'm going to show you some results, numerical results, where you put G equals 0 and only keep G prime. And then you can just solve the whole thing. Well, it takes some effort. Chen-Wan and Ilya have been working hard at it, but we have now some very interesting results. And the conductivity, similarly, is just dictated by the structure of the SYK response functions of what you have to compute. So first thing, let me just show you what happens when you include both G and G prime perturbatively. Then you find that the electron Green's function has a marginal Fermi liquid form, and the marginal Fermi liquid relaxation time comes both from G, from the non-random coupling, and the random coupling. On the other hand, when you compute the conductivity, that also has a 1 over omega form, and there's really no previous calculation that has shown such a behavior. But now the marginal or the 1 over omega behavior in the conductivity comes from the G prime only. The effects of G cancel out. And this is very much related to what I said at the beginning of my talk, that pure, completely clean quantum critical points are perfect metals. And even in this dirty limit, you see this cancellation appearing where the G drops out of transport. All right, and you also get other observed properties like the T log T specific heat, and so on. All right, so now in the remaining few minutes, let me show you the results of just completely solving these equations at G equals 0. That's the simpler case. All right, so this is the usual color plot of the resistivity. Now there's no foot because we're not including the localized effects at all. This is such SYK-like analysis. And so there's linear T behavior here and quadratic there. The model also goes superconducting, and that's the TC. So this is supposed to apply to the overdope side. Underdope has very different physics, not described by this model. So in particular, I want to focus on the optical conductivity. So these are optical conductivity measurements of Wanda Merrill. They go back at least 15 years, but recently, just last year, they published a reinterpretation of the data. And this is just about the time our paper was coming out. And somewhat remarkably, their reinterpretation of the data and our theory are essentially identical. So this is the optical conductivity, the modulus and the phase at different temperature in LSCO. And you notice I had this 1 over this power law in omega, which is around 0.8. In the previous paper, they said it was 2/3 and somehow connected it to omega to the 2/3 that you get in clean non-Fermi liquids. That's incorrect, both experimentally and theoretically. Now the interpretation of this is just a logarithmic correction from 1 over omega. And this is the phase of the conductivity. And this is our computation. And you get, 0.9. This is due to logs coming in the effective mass. And this is the phase. Then from fitting your results to this formula, you can read off the tau of omega and m star of omega. So this is what they did in the experiment. This is h bar over tau as a function of omega for different temperatures. And then when you rescale both with temperature, the elastic scattering, the transport scattering rate scales beautifully. And that's exactly what we find in our numerical computations. The effective mass, as plotted as a function of frequency at different temperature, doesn't scale as well. And at 0 temperature has a logarithmic dependence on temperature, which is exactly what comes out of our theory too. Very recently, so 1 minute left, okay, stop talking. We had a couple of questions. So this is just work, it's still work in progress. We've also computed the superfluid density and the critical temperature and various things, the superconducting state. So this is the, a complete theory, at least in this model, of the onset of superconductivity from a strange metal in 2 dimensions. So we find one unusual feature we haven't fully understood yet, that as you move away from the quantum critical point, then TC decreases, that's fine, but the superfluid density at 0 temperature actually increases. And somewhat remarkably, when I started looking at the literature, that seems to be exactly what's seen in the cuprates in the bulk samples. So notice this is TC going from 1 to 0, so this is the overdose side, TC decreasing as you move up this way. And there's the plots for bulk samples in LSTO and VSCO, which show exactly this type of behavior. We're also been computing Ohm's law and trying to understand the slope of Ohm's law, but that's kind of work in progress. All right, so I'll stop right there. So what I've just described is a self-consistent SYK-like theory of the strange metal here in the extended regime, where bosons and fermions are both extended. I had talked about essentially the theory was as if for the spin density we have critical point, but it works for the other 2 classes too with some small modifications. And as I've shown you, it really fits in detail the whole optical conductivity data that's been around for a long time, and transport and thermodynamics too, and photo emission, I would claim also. More interesting, and I think would be worth studying much more, where we have less analytical control, is what's happening down here, where you have these Griffiths effects from localized bosons, and maybe experimentally also seeing these localized bosons, I think would be very helpful, assuming they're there, in understanding what's going on better. Thank you.
Thank you. There's a number of questions during the talk, but I think there will be more questions. With my friend. You will get mine.
Just a very brief one. You mentioned randomness in stiffness also in K.
Well, we didn't compute. This is in the SYK theory where everything is self-averaged.
But what do you think is going to happen if you also include randomness there?
No, that's a great question. That is, can we solve, measure the spatial randomness in the superconducting state due to the localized bosons? Yeah, we haven't done that. That's quite a bit harder. But in fact, I was talking to Nigel Hussey and various people. They're very interested in exactly that. I'm not sure what's an efficient way to do that yet. But yeah, that's, I think, another interesting direction to look at this further. Yeah.
So before you did this rescaling to the Yukawa couple,
you had this
random singlet, I don't know,
Yeah,
boson.
right.
So, and then you showed some results for the self-energy of the fermion.
Yeah.
Is that a numerical calculation?
Yeah, yeah.
In that picture.
Right, right.
So how does that compare to the picture that you then followed, where you work on the basis of these disordered bosons, where you shift the disorder to the
Well, there are some differences. I mean, so for example, I didn't show that data. If you look at like the boson density of states, in this case, because the bosons have a mod omega propagator and everything is extended, the density of states is actually constant as a function of energy in 2 dimensions. But when we look at the numerically, the density of states of the bosons in the localized regime, it's constant for a while, so that supports that when the bosons are extended, this picture is fine, but then you see a enhancement at low energies. Now, that enhancement in the boson density of states, doesn't quite show up in the frequency dependence or the as far as we can tell, it's still linear. The resistivity looks linear, but certainly one of the differences is this little thing coming out here, this extended non-Fermi liquid phase, which we need to understand better. That doesn't happen in the SYK analysis. So this extended phase here should be compared with the SYK. Yeah, that's the full numerical analysis of the bosons. This is the SYK analysis. It looks quite different. Yeah, so it's still a bit of a mystery why this is still linear down here. Maybe we need further resolution. But experimentally also, it seems to be linear in that whole foot. It's, in this calculation by Eresberg et al., yeah, they have a continuously varying exponent. But all right. But that's an exponent depends on what they put in on the disorder. Yeah.
So could you go back to the plot where you had the various regimes of the localization?
Yeah.
So is the resistivity from scattering off these things different in regime C versus D? Is it already T linear in C and
Okay, I'll let Avishkar answer that. I don't know the answer to that. Yeah, Avishkar. It's linear in both. Okay. All right. Oh, I see. Yeah. You mean these localized, they give you residual resistivity. Yeah. Okay. Well, in addition to some frequency dependent self-energy, I think. Yeah. Yeah, but without precision at this point, I guess we don't know.
But one would expect a continuously varying exponent for the resistivity from the continuously varying Z in the Gapless regime.
Yes, you're right. Yeah, so there should be, it's possible, right? So it'd be great to have more analytical results in this regime.
Yeah, I had a question about the optical conductivity data that was mentioned towards the end. Yeah, so the axes, so I know from your theory you can get this omega linear scattering rate.
Yeah, no, so good point. And, so in fact, yeah, these numbers are huge.
They're huge.
Okay, sorry.
Yeah, I just on the left plot, the linear scaling seems to go up to like 0.4 EV. Yeah. Which is some crazy temperature in terms of the actual like cuprate materials.
In terms of frequency, yes.
Yeah. So I was wondering if you have an understanding of why the linearity should go up to such high frequencies, where we might expect UV physics to come in, right?
Okay. Yeah, I don't have anything interesting to say about that. Yeah.
So in the theory, does it show up that something breaks down when you go to sufficiently high frequencies, or?
Well, there's eventually some kind of bad metal regime, which also has some anomalous power law, which will be, at least in, yeah. So we are studying some of that crossover right now.
Okay, thanks.
But I should say, what I thought you were going to ask is that this h bar t in units, in Planckian units, this is the tau in Planckian units, and the numbers are really large. Whereas in our theory, it's about a 1 at 0 frequency, which is what you expect. So then I called up the authors and said, what about this? This scale seems completely wrong. How did you normalize your K? And they said, yes, there's some mistake. So But this is the published data, and there's definitely something wrong with this overall scale here. That may also affect what you were worried about.
The slope of the T-linear at high
Yeah.
temperature, does that depend on the disorder strength?
Yes, it does.
I see. But experimentally, what's the...
I think you can find experiments where it varies with the disorder, and you can find experiments where it doesn't. But I would say that what we are accounting for is more long wavelength disorder. It's coming from just the dopants themselves, and that's what feeds into delta S and G. Whereas very short wavelength disorder, like some radiation damage, more affects V than G. Yeah, but okay.
And then a related question, so what would act as a cutoff on the effective theory in this case, on this linear behavior at high temperature?
Basically the bandwidth at this point, and then you cross over to it. There's a higher temperature regime where your energy is about a J of the bandwidth, and then you're in some, it's there also, this is one of the problems of this field. No matter where you look, it's linear, but for different reasons. You get the bad metal regime where, again, the resistivity is quasi-linear. And exactly how this crosses over into that is something Avishka has written some papers on, and we're still working on some details in that regime.
But shouldn't the disorder strength somehow, like the mean free path, which overlaps the boson, shouldn't that also act as a cutoff somehow? At least if it's weak disorder.
Yeah, you're asking, is there some regime where you have the clean system behavior? Yeah, we haven't studied that. I mean, it seems to go directly to some, in the regimes we've looked at, to bad metal behavior at high temperatures. Yeah, but the bad metal behavior is also present in the clean limit. There you have strong umflop, and you don't have to worry about all these effects.
Okay, two more questions.
In the first part, you discussed localization of boson.
Yeah.
And I remember you showed some plot with some crossing points.
Yes.
The crossing, isn't a critical point at a finite randomness?
Yes. No, we're keeping, I think, delta S of equal width, and this is just the average value of S. Yeah.
And my question is that, in the beginning, you emphasized that this disorder for boson is the most relevant.
Yes.
Then why do we have a critical point at a finite?
There is still a phase transition. I mean, the Ising model does have a phase transition, but it has an extended Griffiths regime. There's a sharp phase transition as far as we know. I mean, so if you look at this Ising model here, this paper, you know, they do identify a sharp phase transition, but with somewhat similar scaling. Yeah.
Okay, let me ask the last question. About continuity. Suppose you start with a clean case, when you don't have any linearity, neither in self-energy nor in resistivity.
Okay.
Start adding S, randomness.
Yes.
Does linearity first appears at the lowest energies, or it starts coming from higher energies?
Well, I don't think you can just add it perturbatively. I mean, you really have...
You have numerical results, you can vary S easily.
No, but to do anything you know, this is the point here. I mean, we did try that. This was early in the pandemic. We said, okay, let's put in a delta S, and let's just do perturbation theory in it. You get very singular self-energies for the bosons, and the whole thing doesn't...
I'm asking more about the results.
Yeah.
You start putting S and doing calculations.
Well, so what happens when you put in delta S is you get a log omega divergence in the self-energy of the boson. So it just tells you that averaging over S in the self-energy of the boson is a very dangerous thing to do. You don't want to do that. So I should also mention the work of Matt Foster, who doesn't include delta S, but only has random V, and then goes to some high order in the Altshuler-Aronoff corrections to the boson propagator. And he also finds a very singular correction of the boson propagator, where the conductivity, it's a 1 over temperature, it diverges as temperature goes to 0. So that's again a signal that you can't You can't do that. You have to remove this randomness here and put it somewhere else, and then you can do it.
But in terms of the answer,
yeah.
If you look at the pictures, if you compare pictures, say, for self-energy or resistivity, linearity shows up at lowest energies, and then you get extension to something different, or it comes from higher energy.
I'm not sure how yeah, I'll let Avishkar answer that. Thank you. He's going to rescue me.
like a small random mass, probably not going to do that much at high energies. Once you go to very low temperatures, it has strong effects. So I would think the linearity first
extends from the Thank you.
Thank you, Avishkar. Yeah, please refer all questions to him.
Yeah, so a very naive question about this equation though. So suppose I absorb that delta S randomness into phi. Looks like the G will have a very strange distribution, randomness.
Yeah, okay, right? we took Gaussian randomness, but
it's
true, okay. Yeah, that's a simplest assumption.
Well, but
I mean, who's to say, even S is random? I don't know, they're just, S is Gaussian, who's to say S is Gaussian? It just seems this is the coupling we keep, and then there's some kind of certain limit argument.
But a lot of like SYK kind of solution depends on the disorder distribution is Gaussian. I assume.
No, SYK results don't depend on the disorder distribution, at least in the large N limit. They only depend on the second moment. You can take any distribution, you get the same answer.
Okay.
Yeah. The most important thing in SYK is that the disorder is uncorrelated between different points. So the point is this delta function. That's important. But the fact that it's Gaussian is not important.
Yeah, guys, okay, thank you very much.
Yeah, he's done numerics with non-Gaussian disorder and found similar results.